minus 0.1257y in the AZ direction.
This is AZ.
Yeah. What is this?
And it's E of YT, I guess.
What's that?
That can be implied though.
Yeah, but I mean, is there another term?
Volts per, it's just volts per meter.
Is there another term?
This is 5.37.
Yeah, it was just that.
There's a 7 in there. It's 0.1257.
Oh.
But this isn't there.
Y?
Yeah, Y.
And this is in the
AZ. Yeah, AZ.
volts per meter?
Yep.
What do they want?
They just want to find H, but
Why don't we do it? I want to do this. I'm going to take this, put it into a phasor.
Mm-hmm.
Then we're going to take, from the phasor form, we're going to find the H field using phasor, then we'll take it back to the time domain. Y'all with me on this,
Yes.
class? So I'm going to put the two laws that are indispensable. This is plane wave propagation. Do you all agree that this is a plane wave? Simply because it's cosine variation, and the cosine, there's nothing that changes the amplitude of the wave in terms of the magnitude of 100. Y'all follow me? So this is really a plane wave. Do y'all agree with that? It's propagating in what direction, guys, by inspection?
AY.
In the positive AY direction.
Yeah.
Right. So here, we're going to take it to the phasor, but here are the laws. So if you have E and you want H in the phasor form, it's 1 over eta, unit vector and direction of propagation crossing the E field. That's the vector phasor form. And if you have the H field, this will say, and this is for plane waves only, it's 1 over, or minus eta, AP, crossed into H. And those are the two phasor domain forms. We're going to take this into a phasor. Now, y'all realize the magnitude is 100. This is E naught. Everybody with me? Next, the frequency, omega, is 4 pi times 10 to the 6th radians per second. And if you want to know what F is, it's just omega over 2 pi. Next, unit vector in the direction of propagation is AY. Everybody see
It's
this?
just gonna be AY.
Because it's minus AY. Y'all with me?
Yeah.
I mean, it's plus AY, because this is a minus, it's plus AY. You took the words right out of my mouth. And what's beta by looking?
0.1257.
Yeah.
Okay, now that's radians per meter. Now, I'm going to just go through this. We all with this? Next, we can find the phase velocity, if asked, right? That would be omega over beta, correct?
Yep.
I'm just doing this. You help me out. 4 pi times 10 to the 6th divided by 0.1257. What is that?
That's a weird number.
That's a weird number. That's a good number.
999.71126.
Times what?
That's the number.
Can you put it in scientific notation?
1, 2.
Sounds like something Herman Cain once said.
It seems about 1 times 10 to the 7th.
Anybody confirm? So we got 10 to the 6 here.
Also by like times 2 to the 9.
So 99, so we got 9.97, 10 to the 7. That's 10 to the 8. 10 to the 8, right? Take a look.
Yeah.
10 to the 8th meter, about.
Yep.
You give me that?
Sure.
We got that for V phase. All right, now we're going to put this in the phasor domain. Follow me, guys. This is where people mess up. I'm trying to do you a favor here. All right, phasor form of the E field. Vector phase. E naught comes first. I'll write it down. It's going to be E naught. And it's going. This is a lossless, so there is no alpha. Alpha is 0. E to the minus j beta in the direction, it's propagating the y direction, so it's beta y, and it's oriented AZ. Now I'm going to put the values in. I'm going to get out of your way too. We got a fellow named Michael Smith that does the videos in the random class. He does a super job, and he'll shoo me out of the way. But you all follow me on this, guys? All right, what is E naught by inspection, guys? 100, right? Now it's going to be e to the minus j beta, which is, I just leave it as beta. We know what it is, right? And y in the AZ direction. Now that's the E field.
I said yeah.
All right, now there's two things you can do to get H. I want you to hear me. You can take the curl of E, right? And that's equal to, because we have equal, minus J omega mu H. Just telling you this, you could do this. You don't have to, but I want to show you something about this. Do y'all agree with this? Does it say non-magnetic or anything?
Yes, it does.
All right, so if we do
It
that,
says
that's not,
lossless. I don't know if that's
no,
relevant.
that, non-magnetic and lossless aren't the same thing. Lossless sigma is zero. It can still be a magnetic material with mu relative different from zero, or different from one, or epsilon relative. And it's obviously got something different. For this right here, I know one thing. Phase velocity would be c over the square root of epsilon relative at times mu relative. Let me just show you why. In general, phase velocity, if it is lossless now, is 1 over the square root of mu epsilon. This is only for the lossless materials. And lossless means sigma is 0, basically. Okay? Now, if it's free space, if epsilon relative equal 1, mu relative equal 1, and this is a vacuum of free space, then V phase is C is 1 over the square root of mu naught epsilon naught. That is C. That's definition of C. You all with me? Is everybody following me on the speed of light? 3 times 10 to the 8. That is 3 times 10 to the 8 meters per second. Now, we know ours is less than that. So, and I'm going to just use this and bring it over here. So I have our phase velocity will be c over square root of epsilon relative mu relative. Our phase velocity is 10 to the 8th. That means it's equal to 3 times 10 to the 8th over square root of mu relative epsilon relative. Y'all follow me?
So there's no mu naught, or is mu, there's no mu naught, no epsilon naught?
Because it's taken care of with c, right?
Okay.
C is 1 over square root of mu naught epsilon naught. So it's already wrapped into this. You with me on this? If you really want to know how to get this, right here, phase velocity, I know it's omega over beta, right? And when I look at this, the gamma is equal to alpha plus j beta. Gamma is square root of j omega mu times sigma plus j omega epsilon. Now sigma 0, gamma is just j beta, and beta is equal to, right here, it's going to be omega times square root of mu epsilon. If you just look here for a second, you'll see how you get it. Y'all agree that's gamma, right?
Yes.
This would be the general form. If sigma 0, you get this, right? Now, that's just j beta. Beta is this. So if you look at phase velocity, by definition, it's omega over beta. That's omega divided by omega squared root of mu epsilon. Omega's cancel, you 1 over square root of mu epsilon. That's how you get phase velocity. Make sense?
Yes.
That's phase velocity. And just remember, phase velocity in a lossless media is always 1 over square root of mu epsilon, or c over the square root of epsilon relative to mu relative. Back to this. Here's where the ambiguity is. He gives us this right here to work with. All right? What does that tell you just by looking? It tells you what? The square root of mu relative, epsilon relative, is equal to 3. Follow me? We don't know what mu relative or epsilon relative are. What we know is the product. I remember this problem. This is one of Whitworth's problems. If we knew either or of them, right? Okay.
Well, we know mu relative is 1, don't we?
How?
It's non-magnetic. So
It says non-magnetic?
yes.
So it does?
It's
Says-
lossless and non-magnetic.
All right, game over. Then if that's the case, we know epsilon relative, don't we?
9.
That's right. Epsilon relative equals 9 if mu relative equals 1. If it is not, I thought it wasn't, but I thought you didn't say that. But sorry about that. Thank you very much. If that's the case, then we get this. I guess this isn't the problem I'm thinking of. So we get epsilon relative 9. Now look, we don't have to do this darn curl. We could, do you all agree with that?
Mhm.
What do? We just come over here, right? And if we want H, what do we say? Just check it. If we want H, it's 1 over eta. What is eta? Now, please watch this. I'm really trying to do you guys a favor and underscore something. You ready? By definition, the intrinsic impedance of a media is square root of J omega mu over sigma plus J omega epsilon, right? Y'all give me it?
Yep.
But we know sigma is 0 because it is lossless. If sigma wasn't 0, there'd be an alpha here, and e to the minus alpha is y. Follow me? There's not. So now we get rid of sigma, and you can see the j's cancel, the omega cancel, and you get the square root of mu over epsilon. And you can break that out and say it's square root of mu naught over epsilon naught. You can see where I'm going. Times the square root of mu relative over epsilon relative. Just take a look at this and think. I'm glad you asked this. This is a good problem to think about. Ready?
Yep.
What's this?
That's 120 pi.
Right. It's the intrinsic impedance of free space. If you didn't know it, you can plug the values in. Square root of mu naught is square root of 4 pi times 10 to the minus 7. Epsilon naught is 1 over 36 pi times 10 to the minus 8. You mess around, you're going to get 120 pi. So really, this is eta naught times the square root. Mu relative, you said, is 1. Epsilon relative is 9. So it's really eta naught over 3.
40 pi.
Huh?
Or 40 pi.
Yeah, so 120 pi divided by 3 is going to be 40 pi ohms. All right, we've got that. Now we can come up here and we can get this. Take a look. We have 1 over 40 pi ohms. The unit vector in the direction of propagation is AY, right? And we got to cross that with the E field, phasor form the E field, which is going to be 100 e to the minus j. I'm just going to leave it as beta y in the AZ direction, right?
Yes, it's
Okay. Take a good look, and I'm going to finish this thought. Everybody with me? You got it, Jonathan? All right. Do the cross on this one. What do we find H is? Well, it's going to be 100 over 40 pi, right? Now remember, this is phasor domain. 100 over 40 pi is going to be the magnitude. It's going to be e to the minus j beta y, the direction of propagation. We know beta over there is point, whatever it is, 0.1257, right? Now, what about this? We got ay crossed az, yz, x. Correct, class? Make sure everybody see it. You good here? All right, so it's ax. What are the units? Amps per meter, right? There you go. That's H. I'm coming back over here. I want to finish. This is a good problem because it causes you to think about how to obtain eta velocity just by inspecting the inside of that cosine. Now what happens? Well, that's H in the phasor domain. How do you get H in the time domain? I'm going to put it up here. Anytime you have any field in its phasor and you want the time domain form, remember the assumption is it's cosinusoidal variation. So you simply say that H vector as a function of z and t, or y, pardon me, y and t is equal to the real part of the H field vector phasor e to the j omega t. I'm putting it down because believe it or not, this thing is simple, but people overlook it all the time. They don't see the simple way to do it. So here I have the real part. H itself was, so can you give me 100 over 40 pi? Tell me what that is.
0.796.
Thank you. And then it's going to be e to the minus j just beta y is good, right? Times e to the j omega t. I'm going to leave it as omega. We know omega is, what is it, 4 pi times 10 to the 6, right? Omega t, so we know omega, and it's in the x direction. So, obviously, that's a constant. It's 0.796. Then, we've got this. So, we really have e to the j omega t minus beta y, constant. Do y'all follow me in this? If you look at the argument in here, this is really e to the minus, or plus j omega t minus beta y. Now, if you take that, you can use Euler's and break it into cosine omega t minus beta y plus j sine t minus beta y. Do y'all follow me? You with me? Zach? Or not?
Yeah, I got you.
So the real part of that is just the cosine. Therefore, it's cosine of omega t. Omega is given minus beta y. Beta is given. And then it's going to be in the AX direction, and that would be amps per meter. Is that the right answer?
Yeah, that's right.
All right. What else does he ask?
That was all. He just wanted to find the H field. The only question I really had was on that the VP and C stuff.
Huh?
The velocity and the
Does
C.
that make sense now?
Yeah, that makes sense.
All right. Velocity for these is always omega over beta. Beta, you can, if you're ever wondering about beta, you go here. That'll get you. Okay. Everybody? Chase, you good with this? Another one.
I've got more if nobody else has any.
6.7.
All right.
Yeah.
Is that the right answer, by the way?
That's the right
That's
answer. Yeah, I pulled it there.
That's good. And because it exposes you to how to interpret. Let me tell you, I got people that somehow got this number. And it's really the surveys. And the guy will say,
Get you.
we're doing a survey for a certain company. It's like, then why are you calling me? Survey all you want. I did this one time. So there are companies that are paid a lot of money to poll people. I mean, a lot of money. So this one company is being paid by the National Science Foundation to poll people who are professors that have been in the field for a long time about certain things. And this isn't a short poll, like 3 questions. This could take about 20 minutes. So, first they said emails to them. Why are you even asking me this? It's 20 minutes of my time. Do I look like I've just got nothing to do for the rest of my life? So finally, she calls me up. Well, I'll fill out the poll if you send me $100. Well, no. Well, okay. Call back. First time I got it, they sent me. I'm not kidding about this. Or it was either $25 or $100 to do it. After that, the next year they tried it. They wouldn't pay me. Then I'm not doing it. You got to think about this. The amount of time you spend. If it's trivial, a couple of things, I'm fine. But you start spending half an hour to an hour, especially filling out forms and answering questions. Unless you have to for your job, that's a lot of time, especially when you don't have much. I mean, when you're crunching for time. Go ahead.
I got you. 6.7 says suppose E equals 5 cosine of pi times 10 to the 6th t minus 3x
Oh, good.
plus 2y in the AZ direction. And then it's,
And this is volts per meter?
Yep.
Find AP and H.
All right.
Yeah.
Now, this is a good one. So you're used to seeing it. If it was just minus 3x, it would be in the positive x direction, right?
Mm-hmm.
If it was plus 2y, it would be in the negative ay direction. You all follow me? But you got a combination here. So you know how to do it? So when you do these things, what you have to think about is this is usually rendered as in a normal waveform, and I'm going to just say this, when you have anything that's propagating, don't write this down, just listen. There's going to be some constant, E naught, cosine of omega t. That just gives you the frequency information and the type of sinusoidal function. Then it will be minus, and here it's going to be a unit vector in the direction of propagation, and that's going to be dotted with or times either vector k, and I'll get to that in a second, as such, and then trying to say this in a way that's meaningful. Times a, well, let me do it this way before I get too far. I'll do this. And you'll see. So let me just do it. Whitworth does it a different way. Here's how he gets it. I'm going to tell you if you look at the solutions. He takes this and he says a few things. He says, I know that E cross H is actually going to be a vector. It's actually, that right there is going to be the power density, or I should say, pardon me. Yeah, it is the power density of the waveform. If you think about this for a second, now just don't, I don't want to go too far afield. If you look at E, it's volts per meter, right? H is amps per meter. Volt, amps per meter. Volt, amp, watt, right? Volt times amps is watt. Watts per meter squared is the power density. Do you all follow me? This is literally, and I want to go ahead and do this now because this will make more sense. That is called the pointing vector. All right, so it's given this term as symbol script S, like so, and it's called a pointing vector. You can look this up. The units of this are watts per meter squared, and it is the power density of the waveform that's flowing. Now this is something usually I don't go too deep into on an EMAG 1. In EMAG 2 you're going to get it until it comes out your ears, but that's the power density. Sometimes what we do, that's the instantaneous power density. If we talk about the average power density, and the average power density is, you know how when you had circuits, or however you did it, and power was 1/2 the real part of V times I conjugate. Do y'all remember that? Well, this is going to be, you can get from the phasor to me, it's 1/2 the real part of, and it's E vector phasor crossed into H vector phasor, and that will be, the units of this are watts per meter squared. Now that's average power. Power always flows in the direction the wave goes. I want you to just bear with me in this one, because I'm going to make your life a little easy in a second. Y'all with me on this? Okay, I got this and this. I know one thing, E cross H is going to have a magnitude. It has to do with the actual power density, instantaneous power density. But it also has a vector component that is the direction of the power flow. So if we wanted the unit vector in the direction of the actual power flow, it would be E cross H. Now that would be a vector. Do y'all agree with that? Mm-hmm. And then you divide that by the magnitude of E cross H. I think he does it this way.
He did.
That's a unit vector in the direction of propagation. That's another way.
Is that how you want us to do it?
No.
Okay.
I mean, just, you can if you want. I mean, look at this. So we have this thing, right? Mm-hmm. What is it as a phasor? I just want to show you.
5 e to the minus 3x.
E is equal to 5 e to the minus j, and here
Minus j 3x, yeah.
it's going to be what? Or you can put it, yeah, j 3x minus 2y, correct?
Yes.
and it would be in the AZ direction, right? So if you have that as such, you can go ahead and take a curl of that, and then divide by minus j omega mu, and you would have the H field, and then you could do that, right? And I think he does it this way.
Yes.
All right, but here's another way to do it. When you look at this right here, now, and think back that this term really right here, I think you'll see it this way. This is really minus beta, there's some constant, I'll call it beta, times, and this is usually given as z hat, where that would be, I'm trying to say this in a way that's going to be meaningful. Actually, let me back up. I'll show you how to do it in a second. I'm trying to do this in a way it's not going to take you too far afield. All right. So this is really K vector dotted into this stuff, and K itself is going to have a value of beta naught, and then it's going to be a unit vector in the direction of propagation. I'm trying to say this in a way that's not going to confuse you. So this is a vector. And what you get is this. Now, here's how we really do it. Come over here. Actually, let me do it right here and carve up this part of the board. When I take a look at this, I have minus 3x plus 2y. Change the signage on both. In other words, watch. So if I do this, you see you have minus 3x. Call this x, call this y. Instead of that minus 3x, I'm going to make it plus 3x. You'll see this exactly, I promise. So here, that's 3, and this is the x direction. And then the signage here was 2y, now it's minus 2y, okay? Come down here. Was plus, right? This is the actual direction of propagation. Now remember, if you forget about this 2y business, and you want the direction of propagation, change the signage on that, which would be plus 3x. It would be 3x that way, no other permutation, right? That's the direction of propagation. Now, the one thing to get the unit vector here, what I need, AP, right here, the unit vector in the direction of propagation, is going to be the magnitude of this, or it's going to be really the x coordinates, so this is, it's going to be 3ax, and then it's the y coordinate minus 2ay over the magnitude of this thing, over this
13.
one. It's just going to be a magnitude of what? 9 and 4 is 13, right? Square root of 13. So that's going to be a unit vector in the direction of propagation. Can you all follow me on this?
Yes.
Just work with me. And again, the way I always do these, you see what, it doesn't matter how many terms here. It could be x, y, and z. Take the coefficients of x, y, and z and alter the signage. Then go ahead and build a triangle like I just did. That triangle is showing you the direction of propagation. To get a vector in that direction, the only thing, a unit vector, I have to do is take really 3ax minus 2ay divided by the magnitude of the two. You've got a vector in the direction of propagation, right? No curls involved. The other thing is to get beta, or the propagation constant, that's the unit vector in the direction of propagation. Do you all agree with that? Mm-hmm. We've already got an equation for the waveform, so you don't need that. Beta is just equal to the square of beta, really the coefficient of x, and I call this beta x squared plus beta y squared. So it's the square root of 3 squared plus 2 squared, or it's equal to the square root of 13, right? And that will be beta. Y'all with me?
Okay.
Now, you can always get it that way. I'm showing you the trick. You can do this. There is nothing at all wrong with doing that. But there's more work to that. First, you got to find h. Right? Then you got to go and do the cross product of h and divide by the magnitude of the cross product of e cross h. Yeah.
So how do we find eta?
What?
How do we find eta?
We got beta, don't we?
Yes, but we need eta, don't we?
Yeah. How do we have omega?
Uh,
Yeah, it's right there.
All right. So, with me?
yes.
Okay. So if we have omega and we have beta, what do you know we have? Phase velocity, right? Is it lossless? Just look at the
It
wave.
is not. It does not say.
It is. If it doesn't have e to the minus j minus alpha z or alpha y, it's lossless, right? If it was lossy, you would have this. It would have some e to the minus some constants, and it would be a function of z and y. Do you all follow me?
So if it's just a constant magnitude, we have just a normal number out front.
That's lossless. All right, lossless. Now, look, what's the phase velocity? Work with me.
It's just going to be
Remember?
omega over b, you know?
Omega over beta, right?
Beta.
Let's find out what it is. What's omega? Pi times 10 to the 6. What's beta? Square root of 13. What is it? I don't know. Tell me.
So the system is lossless.
Yeah, but what's this? This thing ain't lost. I mean, this is a slow wave.
Okay.
I don't know.
Is this 10 to the 6, really?
Yep.
Yeah, it's
I don't know, Whitworth doesn't usually do this kind. This is a very slow wave. It's of the order of 10 to
It
the
is
6. What?
It is 8.71 times 10 to the fifth.
All right. Meters, that's slow. And what else does it say anything about non-magnetic?
Nope.
Anything about epsilon relative or mu relative?
It literally just says E. There's E. Find AP. Find H. Actually, nothing. else.
Find H?
Yeah. Find the
It
H.
says find H
Find
and
the H
the-
field. Yeah.
and
All right,
the,
that's not a problem. But we've got the direction of propagation. Is that right?
That
Does he
is
have-
that is what I got. Yes, and that is what he has as well. Yes.
All right, that's the direction of propagation. And then he asked for the H field.
Yes.
Now he probably does a curl of E,
He does.
which is a waste. It's a plane wave. It's propagating. Just do it this way. We got the direction of propagation. I'm gonna erase this. Just keep watching. I know I'm putting out some theory here, new theory, but this I think makes life easy when you see how to actually go about it in a vector direction. You don't have to do all these curls. Curls will drive you nuts. Cross product in curls. You don't have to do this. So look, what's E field of phase of work with me. E field of phase of is what? Well, the magnitude, what was it again? 100?
5.
5. All right, 5. Then we have what? E to the minus j.
3 plus 2. 3x plus 2y in parentheses.
It's gonna be
Minus 2y.
3x. It's positive 3x. or
3x
minus
minus 2y.
you're right.
All right. Right?
In
AZ.
the, in the AZ direction.
And it's AZ. Did
Yep.
you do it this way? Or no?
This is
That's
how
how,
I did it.
that's how I tried to do it.
And then
Wasn't-
I eventually got that,
Alright.
and then I didn't know what to do for eta.
No, I mean, this is one of these things, he's assuming something. If you look at this, we have a phase velocity of what?
Oh well, I guess if you take
5.8 what?
It was 8.71 times 10 to the 5.
8,
8.71 times 10 to the 5.
and that's meters per second, right? It's lossless, you all with me?
Yep.
So that means it's C over the square root of mu relative, epsilon relative. Now, thing is, if he doesn't nail down one of the two of those, you can't get eta.
I was also good, but he does it by taking the curl of E or H or whatever.
He takes the curl of E and sets it equal to minus j omega mu, right?
Yes, it has to be so. Mu
Yeah,
has
but
to
he
be
assumes
mu naught.
it's mu naught.
It is.
It doesn't state it's mu naught. If it was non-magnetic, it would be mu naught. If he makes that assumption, then we can just say this is square root of epsilon relative. You agree with that?
Yes.
If he assumes mu relative is 1, then now we can get what? Epsilon relative here for our media would be what? C over this form. It's a big value. 10 to the 5th squared. So it's really equal to 3 times 10 to the 8th over 8.71 times 10 to the 5th squared. This is huge.
Yeah, I got about a 1.19 times 10 to the 5th.
Huge. There's nothing that big normal. I mean, there are exotic materials that you can take down extremely low temperatures that maybe can get something like that, but that's ridiculously large. What it really says is this material can hold about 10 to the 5th times as much energy per unit volume as free space, which is insane. I'm sure a lot of people would love to have that for capacitors, but it ain't so. There's nothing. I mean, exotic materials may be at a super low temperature, but not at any actual temperature. So now that that's the case, now let's see if you guys get this. Since you asked that we've got E, right? But in order to get H, just look. H is going to be equal to 1 over eta, right? Unit vector in the direction of propagation crossed into the E field. That's what it's going to be for a plane wave, right? We got the unit vector in the direction of propagation, right? We've got the E field in the phasor form, right? Right there, correct? But, I'm sorry, what don't we have? We don't have eta, right? And what is eta? Eta is this. So that means when I look at the eta, I mean, that's eta. I'm sorry, that's epsilon relative. So what's eta? Well, it's square root of mu naught epsilon naught times square root of mu relative epsilon relative. Since we're assuming, and he does, mu relative is 1, right? Then you get 120 pi divided by the square root of this thing, which is huge. Tell me what this is. Square root of 1.19 times 10 to the 5th. Grayson, did you do it this way?
So I did not assume mu is mu naught, and so I could not solve it.
Well,
so
you can't, unless you, because
And
he has to do it with mu naught and the answers.
And that's where I got stuck.
All right, are you with me on this one?
Yes.
It ends up being 1.09.
That's small. 1.09 ohms per meter. Oh, really? Sorry, just ohms, pardon me, ohms. 1.09 ohms, okay. Now let's get the H field. Let's see if we get his H field. So that means our H field right here is going to be 1 over 1.09 ohms. 1.09, man, that's about 1. AP, remember what AP was? It's somewhere over there.
It's 3 over root 13.
It is.
AX.
The decimal form.
AX, huh?
The decimal form is minus point.
No, just 3AX minus what? 2?
2AY.
AY over square root of 13, right?
Mhm.
We'll do it this way. And we've got to take that and cross into the E field, which is 5e to the minus j. These are just things that are going to come along with this. 3x minus 2y, but it's in the AZ direction. Again, take a moment. Do you all agree with this?
Yes.
The only thing I'm doing is rewriting the obvious. Got it, Hayden? Jonathan, Chase. I'm making sure. What, is it Jason?
Jackson.
Jackson. Sorry. Jackson? Okay. What is that one fellow's name that's for national? That's in there. Not the Chinese guy, the other.
No idea.
Gosh,
I have no clue.
I got a whole bunch of his homeworks. He hasn't dropped, at least last I looked.
He hasn't been here since the last exam.
He hasn't been at the home or the last quizzes. He's been AWOL. Anybody see him in the building?
I've not seen him. In
I
the
need to
building
report him if he's really missing. I'm not kidding, because we've had students that literally died in there.
once.
I mean, honestly, I'm not kidding about this. It's horrific. I mean, nobody checks on him, so nobody knows. I've never had one in my class that died. Thank God. At least I don't know. All right. Coming down to this, what happens here, guys? What do we get?
Oh.
Just do me a favor. 1 over 1.09 square root of 13. I'm going to leave that out in front, and I'm going to put the 5 out in front. I'm trying to take care of all this constant stuff. Follow me? Next, I'm going to take the exponential stuff out in front. E to the minus j, 3x minus 2y. That's out in front. Now I need to take ax cross az is, x cross c is minus
8y.
Right. So we're going to have minus 3ay, and then we have ay cross az is ax,
So
right?
minus 2a.
Minus 2y?
It's minus ax.
2ax, right? And
That's it.
so that's h in the phasor domain, right? How do you get the time domain? Just tell me.
You just convert the magnitude, and it's going to be the magnitude.
Well, you take this and you multiply by e to the j omega t. just hear me, right?
Yeah.
And then you
it'll
take
become
the real
cosine.
part. Now, when you take the real part, here's the deal. You're going to have an x and a y component. You're not going to have just the one component.
Yep.
Is that what he has?
Yep.
Can everybody do that? In other words, we might as well do it. H in the time domain. All right, so it's for the x components, minus 2 times 5 is minus 10 over 1.09. Let's get one component at least. Over
Do you want the number?
In a second I will, or square root of 13. Now look, this is common to both, this exponential, so when we multiply by e to the j omega t, take the real part, we're going to do cosine of omega t, and it's going to be minus 3x plus 2y, right? You all with me, class? And that's the cosine. The sine, it's going to be, and this is ax. And then the other one is going to be, holy mackerel, minus 15 over 1.09 square root of 13, right? And then we're going to have, same deal, cosine of omega t minus 3x plus 2y. And this is going to be in the ay direction. Can you give me the value of this thing?
It's negative 2.53 in the ax.
Is that what he has?
Yeah, and it's negative 3.8 in the ay, and that's what he has.
Yep.
All right,
Multiplying
I'm
the
just
side
going to
gets it.
leave it like that. Can you all follow me?
Yeah, that's
Jonathan?
that's what he got.
All right, I want to tell you one other thing about this. So a logical thought is, Dr. Baginski, would you expect us to do E crossed H over the magnitude of E crossed H? If your heart desires to do it, it should. Easiest thing in the world is what I just showed you. Just look at that triangle I drew there. Make sure you know how to do that. It's trivial then. Y'all follow me? And it's, I mean, there's just a lot of shortcuts in electromagnetics to get to the result. I've been around this, I have done this for a long time. At the advanced level 2, almost everything comes down to a very clever trick to reduce the complexity. Because honestly, brute force and this kind of stuff will drive you out of your mind if you have like 50 problems. Okay, another one. That's a great problem.
That won't work.
Let me erase this.
Are we doing any more material?
We don't have to, but I'm trying to show you tricks. You know how this is a trick to beat that E cross H or magnitude E? I'll show you some tricks to beat a lot of it. One of it has to do with conductivity. When the conductivity becomes a function or a value, and it's a good trick.
I still have one more question, so that'll probably run up the class for today.
All right, hold on. Let me erase this. Go ahead.
Oh, but I was gonna say, on Monday, you did say we're doing a review day? I just can't remember.
What?
On
Yeah.
Monday, review day? Okay.
Are you going to do it? I'm going to, I'll level with you. Nobody here is had me. Chase, you sort of had me. The one thing you need to know is I build all my exams based on tests. Based all my exams and tests based on the homework and the lecture. Obviously, the homeworks that we go up on the board are a real valuable resource. But if you look at just look back. You've had me for random endness, so have you. Everything comes from the homework. There's nothing that I don't use the homework to build on. It's not something out of the blue. And There are professors that do that. Yeah, I mean, they go through the theory, give you problems, and the next thing you know, prove that this is greater than that. It's like, you never asked me to prove in my life. I won't do that. All right.
What problem do you want to do?
6.11.
611?
Yep.
All right, hold on.
I don't remember why I wanted to do it. I just wrote it down.
611. I'm glad you asked that one with the X and Y code. That's a good problem. And it's, once you see it, it's easy to see. Go ahead.
This one looks simple. I don't know why I asked, but we'll see. H equals 100 cosine omega t
100 cosine of omega t
minus 10y.
minus 10y. Milliamps per meter.
Yeah, in the AZ.
All right, in the AZ direction, go ahead.
Find propagation velocity, angular frequency,
All right.
and electric field.
So first they want phase velocity. All right, then they want what?
They want omega,
All right, omega. And what else?
E field.
E. No problem. Is this in free space?
Lossless, non-magnetic.
So,
Oh, he also gives epsilon relative. True.
so it's non-magnetic, mu relative.
Epsilon
Non-magnetic,
relative.
mu relative is 1. He gives you epsilon relative is what?
16?
60?
16. Bless you.
All right, bless you. All right, he wants that, he's giving you everything he's asking
And
for.
so
right?
it'd be, I didn't know this equation before, C over the square root of
Yeah,
16.
the only thing you have to do is say
C over
phase
4.
velocity really is omega over beta, but if it's lossless, it's just 1 over square root of mu epsilon. You can prove that by going back to gamma. Y'all with me? Because alpha is 0. Y'all agree alpha is 0? Oh, alpha. What? There's no e to the minus alpha anything times y, right? So if you look at this, what does that mean? As you pointed out, it's really, this is c divided by square root of mu relative, epsilon relative. Well, that's 3 times 10 to the 8th over, mu relative is 1, square root of 16 is 4, so that should be the phase velocity. It's 0.75 times 10 to the 8th, or 7.5.
And that's correct.
Okay, you with me, class?
Yep.
Chase, with me? Next, how do we get omega?
It'd be V.
Hint, always
Yeah.
look at the
Be
coefficients.
beta.
So we know phase velocity is omega over beta. We have phase velocity, we're looking for omega, and we have beta, don't we?
So it'd be beta VP.
So look at this. Omega is equal to phase velocity times beta. Can everybody see beta is 10 here, class? Beta. All right, just write that down. I don't mean to. I'm trying not to go too fast,
No, it has been helpful.
but I have to use the bathroom. So, so it's, what is this? 3/4 times 10 to the 8th, right?
7.5, yeah.
Times 10, right? So it's 7.5
Times 10 to the 8th.
10 to the 8th radians per second, right? Want to take a guess at what E is? First, which way is this wave propagate? I'm going to show you a
It's
trick.
going in
You ready for a real trick? You're going to bless me in a second, I think.
Plus Y.
I hope.
Go
Ready?
positive Y. Huh?
It's going the plus Y direction. Now, here's the deal. Remember, E crossed into H divided by the magnitude of E crossed H is really a unit vector in the direction of propagation, right? One thing I want you to take from this, if you want to get the direction of H and you know the direction of propagation, you look at the direction of E and you can get it this way. Unit vector in the direction of propagation is really going to be a unit vector in the direction that the E field is polarized, crossed into a unit vector in the direction the H field is polarized. That will always give you, for a plane wave, the direction of propagation. I'm telling you, I'm helping you here. And whatever two you don't have, or whatever one you don't have, you can get from this. Can you all follow me in this? So, go with me on it. Unit vector in the direction of propagation is AY. Can you all see that? Just by looking. All right, now, that's equal to a unit vector in the direction of the E field. Well, we don't know that, do we? crossed into unit vector in the direction of the H field. Which orientation is the H field by looking?
Oh, H field is an AX.
AZ, is it?
Wait.
Isn't this?
Sorry. I thought you were acting for the E field. My bad.
No. H, right?
Yeah.
Y'all follow me?
So it's gonna be.
I want to just put this down here. AX. I mean AZ, pardon me. AZ, my bad. So now, I don't care how you do this. We can rotate these. If we can, you can shift everything to right. You can say AZ is equal to AY cross AE, or you can shift it again. You can get AE is what? Take a look at this. If this is Y, right? This has to be minus AX, doesn't it? Think about it. If it was AX, we know it's got to be X. If that's Y, this is E. If it's AX cross AZ, it would be minus AY, right?
Yeah.
Yes.
That means AE has to be minus AX, correct? So AE equals minus AX. See if that works. If we have E is minus AX crossed Z.
Wait.
What?
So the H field propagates in the AZ direction.
No, it's oriented in the AZ.
Yeah. But the
It's propagating the Y.
Yes. The wave is propagating in the plus Y direction.
That's right. AP is plus Y.
And so wouldn't it be AP cross AZ,
Well, just look up here.
which is
Direction of
Y
propagation is AE cross AH, right?
Yes.
All right, that's vector direction, not the propagation direction, the vector orientation.
Yes.
All right.
Yes.
What is the vector orientation of H? It's Z, right?
Yes.
All right, so this is Z, this is Y, right?
Yes.
This has to be plus or minus AX.
Yes.
Has to be with that. All right, if it was plus AX, what would happen? AX crossed AZ is minus AY. No, this has to be minus AX. Y'all with me?
Yes.
So it's minus AX is the direction of the E field. Now here's how you get the rest of it. I'm going to go right here. Be attentive. You'll find me.
It's because of the reason why it's because of the minus in the equation. E equals minus eta AP cross H.
If you want to do it that way, you can. Yeah.
That's where it was coming from.
Yeah. You can do it that way. Bless you. Bless you. Hold on. Let's get the E field. I'll show you how you do it. All right. I want to do it right under here. First, E field will have, listen to me now, this is losses. So the E field is going to have the same spatial and temporal signature. It'll have the same cosine form. You all with me? Now the magnitude of the E field is going to be this times eta. With me?
Yes.
But you got the direction, it's got a minus sign in the orientation. So you can put minus eta, we'll get to in a second, times 100 times cosine of omega t minus 10y milliamps per meter, and it will be in the AX direction. I took the negative AX and I put the negative sign here.
Yep.
And what is eta?
It's the square root of mu over epsilon.
Right, 120 pi, right, divided by
4.
square root of 16 or 4, so
30 pi.
30 pi. So this is 30 pi minus 30 pi. And that's milliamps, so milli is 10 to the minus third. So might as well just do this. Divided by 1,000. What do you get for the coefficient there?
Negative 9.4.
9.4?
Yep.
Is that right?
That's what he has in his answer.
9.4 cosine of omega. You know how to get omega, right?
Yep.
Yeah,
I
where
don't
you
remember what it was, but minus
It was 7.5 times 10 to the 8.
amps per meter, okay, in the AX direction, and that should be the answer, yes.
Yep.
That's a good problem. You know what? I'm trying to show you the tricks. I wanted to show you this thing. That's a trick. It's an easy trick to remember. I'm almost out of time. Another one?
Nope.
That's all I have.
That's all I got.
Okay. I've held you over a few times. I guess I can break it up. That way you'll be on time for your bus, and I'll be on time for the bathroom. Boy, I hate to miss that. classes over the course of my career. I've been here 37 years, going 38.
How large is this